Wait a few more minutes. Any questions from previous class? So you missed last week.
I missed.
So you can get the video from him. So anybody wants the video, you can talk to. Any question with the homework? I was giving them, so like that thermal expansion, you may need to know this Gaussian integrals, right? This one. So one thing we know is when n is odd, this is 0, right? When it equals even, you have to find this. These are called the Gaussian integrals, right? So you can find for x squared, x4, like that. So in that problem, thermal expansion problem, you get terms from x4, right? So that's the non-zero one. Remember, in that problem, you have to do the integral for average energy, right? So that is basically the average expansion, that is x times your, so this beta times this terms. In the class we did this one, right? So that's why it was 0, right? So if you use, but in this one I gave this one as some x squared plus some x cubed plus x4, like that. So just expand this one. This you can write as e, say minus bx cubed plus x4, something like that. Expand this one as 1 plus x. So that means this becomes minus 1 plus beta x cube or whatever x4, right? So then now you will see where you get the, here you get odd number, here you get the even number, here you get the odd number. So that's very simple. Otherwise people might go wrong direction. This is two-liner, so we can get down.
There is a direct.
Huh?
There is direct solution in book.
Book has the solution is given, yes, but they didn't show the
steps.
Yeah. Where's everybody else?
Third step thing. The third step thing.
What's that? On time. Okay, so last time we talked about mostly this very important phenomena called the Fermi energy, right? So then Fermi energy can be related to many Fermi quantities like wave vector, Fermi momentum, Fermi velocity, Fermi temperature. So these are typical values for ordinary metals. So for example, Fermi velocity is like 10 to the power 6, that's meters per second. But if you take like graphene kind of materials, they have very high mobility. This number can be 10 to the power 8. So that's very special case. So like when we talk about Fermi energy, is not just hypothetical thing. So right, it's really something that you can observe in an experiment. Here is a simple experiment. So here we use some material. So this is maybe from aluminum. So if you take aluminum and try to ionize the material, ionize means you just try to remove one electron from, say, your L3 state. Everybody familiar with this L1, L2, L3 states? Probably. So typically you have K shell, L shell, like this is a principal quantum number, right? So basically n equals 1, that is K shell, n equals 2, L shell, Lm, like that, right? If you take n equals 2, that means you have L goes from, L has 1, right? N minus 1. So then your ML can go like minus 1, 0, plus 1. That's how you get the SP orbitals, right? So L1, L2, L3 means, so later we are going to talk about this one when you do the Hund's rules. So if you take just the S1 coming from L equals 0, right? So then if you take p orbital, so p can be hybridized with s orbital, like ls orbital, right? You have angular momentum and the spin. So that means if you have L equals 1, it can be L plus S and L minus 1. That means you can have this P either half or P 3 by 2, right? So that's what we call the L1, this is we call L2, this is we call L3. These are the 3 excited states. So now in this experiment, we are going to ionize. That means I can use like high energetic electron beam to remove one electron from, these are co-electrons, right? So from that co-electron, I am going to remove one. Then what do you have? This is an empty state, right? So now if we look at the valence band, because here we are talking about aluminum, we have nucleus, then we have the co-electrons, then have 3 electrons in the valence band, right? So these co-electrons are what we are showing here. You can have K shell, L shell, and like that. These are all the valence band. Remember, in the valence band, we talk about having states from the, because that's the Fermi C, right? Fermi electron gas. So you have energy is up to Fermi energy, right? These are field state in the valence state. So then every state above that one is empty, occupied and unoccupied. In the K space, that's what we showed, right? So up to this KF, you have all the field state, everything above here is unfilled. So now if you look at this one, so we remove one electron from here, you have a empty state here. So now from this valence state, they are at high energy, right? They are going to come down to the empty state. Suppose initially you have this state, right? So when it comes down, usually they emit that loss of your delta E is coming like some h nu, right? This is actually soft X-ray region. So from, suppose when electron from here to here comes, you get some energy. So that is the energy. If you measure that intensity, suppose that is this one. Then if electron comes down from here to here, then you get little high energy, right? So if you get from here to here, you get this one. If it comes from here to here, you get the, after that what happens? Do you have any state here? No, right? No electrons about. That means there's no energy, then immediately that energy goes to 0. So that means what is this corresponds to? Directly the Fermi energy, right? So this is how people immediately can look at the Fermi energy. So here's the real experiment. You can see that energy of this outcoming radiation. This is what we are measuring. You remove electron, you have the empty state. Now you are looking at the outcoming X-ray spectrum. So you will see it's going up and immediately it goes to 0. So here is the real experiment. This is from aluminum L3. L3 means you ionize this one, right? You can do, if you use different energy, you can ionize this one, then you can get the L2 spectrum. So here you can see what is this one. These are electron coming from this state, right? Then when you come here, That means this corresponds to the Fermi energy, right? So after that you can see sharp drop to zero. If you measure the energy from here to here, you get the Fermi energy. That's very easy way to calculate the Fermi energy, measure the Fermi energy of metal especially. So then you can compare this one. Remember, we know how to calculate the Fermi energy from this equation, right? If you know your Kf using this one, if you know the free energy density from, if you do this one, if you calculate EF actually for aluminum, you get about 12. So measured value is about 13. So that's close enough. So this soft X-ray spectroscopy is very easy way to directly measure the. There are so many other ways to do that one. This is one of the ways. Okay, so now today let's use, actually you can derive almost every property of not only metals. Later we are going to talk about semiconductors also. To measure, calculate all the properties, you need to know the density of states, right? So for, let's see some simple things to calculate. How do you calculate the average energy of a free electron gas? Free electron gas. If you want to calculate the average energy, how do you do the average energy? Typically, average energy you calculate as, you calculate your energy, right, times density of state times dN, right? So then divide by the total number of electrons. That's the average, right? So that you can write as E times, what is dN? We know dN is dE times dE, right? That's the definition. No dk over dk, any of this, right? So then I can write dN as dE times dE divided by dN is basically dE times dE. That's it, right? So what is the integral limit? Can you tell me what is the integral limit should be? E? You have to go from 0 to only Fermi energy, right? So you don't need to go any, because we know it's only filled from your standard, the 0 value up to EF, because here you don't have to, right? So now we know this dE. Everybody remember, that's a big free factor. So after that, what do you have? For 3 dimension, it's very important to know. For 3-dimensional case, your density of state goes like some constant times square root of E. Because the density of state is something like this, dE times E. If it is a 2-dimension, this is a constant. It doesn't depend on the energy. If it is 1 dimension, it's called 1 over square root of E. If it is a 0 dimension like quantum dots, it is actually delta functions. So in this case, so you have some free factor that has the mass or the Planck constant, everything there, right? But here we are going to calculate some ratio. So we don't need to know that value, right? They cancel each other. So only thing you need to know is just plug in here that constant times. If I do this one, you can calculate this average value. It's basically you have E is now A times this one, right? So if you do that one, A comes out, so 0 to EF. Then what we have here, dE has E square root of this one. This has E, that means E to the power 3 by 2, right? So here you have same A, that's why we don't need to know that one, they cancel each other. Here you have dE is simply square root of E, right? Very simple integral, right? So here when you integrate, what do you get? 5 over 2 divided by 5 over 2, that's why you get this value. If you do this one, this becomes 3 by 2. This one, you can see A, this one cancel. If you do this one, you get 3/5 of your average energy is 3/5 of your Fermi energy. So typically Fermi energy is your that highest filled state, right? If you calculate all the electron, the average value is little bit more than half So can you understand why it is more than half? Just look at the density of state curve. So it is this shape, right? If it is something like this, what is the average value? This is EF, right? The average value is half EF, right? So you can see this is little bit more than that half value. That means it should be little bit more. That's why it is 0.6, not 0.5. You can understand why. So average value is about 0.6 of the Fermi energy. Right? 3/5 means 0.6, right? Yeah. Rather than 0.5. Okay, so next thing we want to talk about, these are all about metals, right? So if you consider metal, this is the free electron gas. You have a lot of these electrons. So we are talking about this free electron gas, right? These are all electrons. So, and also we have ions, right? So, but these ions are immobile. Only the electrons are moving here. So, ideally considered, each, suppose ions and electrons, they have similar concentrations, right? Suppose if this one gives one charge, then you have one electron, this is singly ionized, right? If you give two electrons, you have two electrons, then this is doubly charged, right? That means really equal number of positive and negative charge. What do you call that kind of charge distribution usually? It's a plasma, right? So this have like equal concentration of positive and negative charge. So that means you can actually consider this free electron gas as a kind of plasma, because inside we have the ions, but they are not moving. So now, since we have these charges, they can easily respond to any external electric field. So just imagine if I consider this free electron gas as something like this. I have all these electrons here. N is my number of electrons per unit volume. N means number of electrons per unit volume. So now just imagine if you have some kind of electric field. So then this electron will respond to the electric field, right? Here you have charges. If you have electric field, we know you have a force given by E, right? So because of that, these charges tend to move, right? So we call this a polarization. Your charges are going to be slightly separated. So suppose if I consider this geometry, if I have area A, cross-sectional area A and length L, that's where all your electrons are here. So now suppose these electrons are kind of moved by distance x. That means if electrons move to one end, the other end becomes less negatively charged, right? So that means this becomes positively charged, this becomes slightly negative charge. Now you have two charges but equal, right? This is plus q, this is minus q. Then what do you have? That you have dipole. So dipole moment is always from negative to positive. If the electric field is this way, no, so actually electric field is this way, right? That's why negative charges are moving that direction. So then I can calculate the dipole moment. Dipole moment is given by what? Charge times distance, right? So now in this case, I can write the dipole moment by the charge. This is the charge. What is that charge? You can easily calculate charge by, you can calculate if you know the, no, so actually in this case, yeah, so this is x, right? So this is the middle part. So this is x. So how do you calculate the charge in this part? What is the volume of that part? A times x, right? So what is the charge density is n. This will give you the total number of charges. If you multiply by charge density, that is my q, right? So AX NE gives you the charge. That is this one. AX N times E, that is this charge here, right? So if you, then the dipole moment means from here to here distance, right? That is L. You just, P is Q times D. So if you multiply by T is L, that is the, so remember dipole moment is always from negative to positive. That means it is negative I direction. So now, everybody remember the word polarization? Polarization means number of dipoles per unit volume. So polarization, later we'll talk about the polarization means total number of dipoles per unit volume. So usually we call this a capital P. So then I can calculate that P by this P divided by total volume. What is that one? P is this one divided by total volume is A times L. If you divide, you can say A and L cancel, you get minus NEX. That is the polarization. So now let's go back and talk a little bit about this polarization. Actually, this is true. Same thing applies for the magnetism also. If you have any, we call that, say, dielectric material. So if you have some external electric field, polarization is always opposite of that one, right? So typically polarization is always opposite direction. So then because of this external electric field, you have some this polarization happening inside, right? Then what is the effective electric field here? That is, we call usually this displacement vector. So that is given by that external electric field. Typically this is in the vacuum, right? That times plus that polarization. That is the effective, the electric field inside. This is the external one. Then inside there's some reorganization of charges, right? That will give you the polarization. So, but P is always negative of E. If you take a magnet, same thing. If I have a external, say, magnetic field H, then inside we have something called, exact like P, we have something called, anybody remember? Magnetization. That magnetization can be either this way or this way. That's the difference. Here polarization is always opposite of P. What is these two are called? Anybody remember? If it is in the same direction, we call it paramagnetism. If it is in the opposite direction, we call it a diamagnetism. Actually, the ferromagnetism also kind of paramagnetism thing, right?
But it's only up to the Curie temperature.
What's that?
But it's only up to the Curie temperature.
Yeah, there's something called the Curie temperature, Neal temperature, like that. So anyway, that's in this case again we have effective field we call B. The B is given by external field mu 0H plus or minus same, right? A very similar situation. This displacement, the displacement vector is more like E and P here. Effective magnetic field is like external field times magnetization. Very similar. Later we are going to talk about these things in details. Right now we only concentrate on this one. Okay, so now what we calculated was P, right? So now using this one, now we are talking about metal. Anybody knows what is the electric field in a metal?
Zero.
Should be zero, right? So that's why we use metals as this the Faraday cage, right? Inside the metal, your electric field should be always, total electric field should be zero, right? That's why if you have a metallic shell, all the charges should be always the outside, right? So you cannot have anything inside. So if you have inside, you have electric field, right? So, but if you have cavity like that, then you can have electric field the charges here, but your effective electric field would be 0. So here it should be 0. But anyway, just remember, if you have a metal, inside the metal your electric field is, effective field is 0. That means in this case your D will be 0. Then you can calculate P in terms of your E. So then if you write this one, so we write D equals epsilon 0 E. P is, we know it is negative, right? Negative NEX times NEX, right? So yeah. So then from here, since D is 0, we calculate E as NEX divided by epsilon 0. Is that clear? We know that electric field is in the opposite direction. Okay, so now we know E. So then if you take this free electron gas, if you take one electron here, we know it is experiencing this force E, electric field E. What is the force then? E times E. If you know the force, then you can write the Newton's second law, right? Mx double dot equals minus E times E, right? So then what do you get? Mx double dot equals minus E. E means now Ne over epsilon 0 times X. What is that one? If you write this one, I can write that X double dot equals minus E Ne square, right? Ne squared over M epsilon 0 times X. And what, remember this one? What is that equation? Simple harmonic oscillator, right? X double, this means D squared X over dx tt squared equals this one times X. Usually we write this one as omega squared, right? Say omega naught squared. So then we know how to write the solution, right? This is basically some oscillations. So this is very important. If you have a metal that has a lot of electrons, if you have some like electromagnetic waves, what is electromagnetic wave means? It has a electric field and magnetic field, right? That electric field will couple to those free electrons, so that will make oscillation. That's what we usually call this plasma oscillations. Here I think this you can follow this one. So this is more like that spring constant problem, right? Minus here. So if you do this one, we call this one, say actually they call this omega p. So omega p squared is actually, omega p is Ne squared over epsilon 0 times M. You can see this omega p increases with density of your metal, right? For example, if I take monovalent metal, say lithium or sodium, so that has a smaller number, right? One coming from one atom. If you take aluminum, that has 3 electrons, right? That means you get larger N. But also it depends on the mass. If you take lithium, its mass is smaller. If you take aluminum, mass is larger. You can see how they change. So now we know these plasma oscillations. These are really useful. Actually later you will learn, if you have this kind of oscillations, actually they can even enhance some this inelastic and like Raman. If you are looking at the Raman, if you can put some, suppose you have some material that has kind of weak Raman scattering. If I can put some gold, silver nanoparticles onto this one, so then because of these plasmons, right, they are making these oscillations, that the laser light make stronger coupling, and that signal can be enhanced by several orders. I don't know whether anybody has heard about surface enhanced Raman, SCR. So if you have some material with weak Raman features, if you can decorate this with some, say, metallic particles like silver, gold, the Raman signal will be enhanced by several orders. You can get huge signal.
You have to do it in some particular pattern?
No, so just disperse it, yeah. Okay, so like I said, now you can make the connection. You had photons, we had phonons. What was photon? Photon is simply electromagnetic waves, right? That has this energy given by h nu. So, but you can have this quantized energy state, right? That goes like n times h cross nu, right? So if you remember, these are basically electromagnetic waves. Remember, these are photons. Then we talk about phonons. What are phonons basically? These are elastic waves, right? Basically. So these atoms are vibrating, then you have these elastic waves. But they are also quantized in terms of n h cross omega. This is the oscillator frequency, right? These are also quantized, but these are elastic waves, right? So now we have new quantized states called plasmons. So these are also electron vibrations, right? These are atomic vibrations. So these are basically the electromagnetic waves, right? So plasmon, these are basically electron oscillations, because like I said, these electrons in the free electron gas, they are oscillating with this plasma frequency. So they also follow this quantized states given by n times h cross omega p. Omega p is given by this value. So these are, we call these are plasmons. So actually these plasmons can be, if you have a material, plasmons can be some surface plasmons, because outside you always have a lot of electrons. Then also in the bulk also you can have some plasmon. They are called the bulk phonons. So, but they also can have this quantized states, n equals 1, n equals 2, like that. Not like half and things like that. Actually people have observed that kind of plasmons. So here what they do is they have some electron beam coming through the sample. So first you send electron beam with some known energy. Then you have a detector, you are looking at what is the energy of the outcoming that electron beam. So if you look at this one, you will find some loss of energy. If you look at the change in your energy, that is exactly equal to h cross omega p. So actually this is some of the results. So if you can see, this is, it's hard to read that, one coming from silver, one coming from aluminum or something. If you look at this one, so actually there are two energies here. So one for n equals 1, right? First one is n equals 1, but that has two peaks very close to each other. These are corresponding to the surface and volume plasma. Then when you go to n equals 2, then you see same thing. So again, this you can see here, this is first, if you look at this one, first one, second one, third one, you can see this is the quantized states, right? So that means this is more like if you have one plasmon, so that means this is the plasmon, because this electron energy is used to excite this plasmon, right? That's why you lose the energy here. But if you have two plasmons, that means that's why you get me two of them. But they all going at equal spacing. If you look at this one, so if this is 10, this happens 20, 30, 40, like that. So these plasmons are real things. Here you can see they have measured this plasma, this delta E, that means this one minus this one, if you measure that one, that should be the plasma frequency, right? The difference, the plasma energy at cross omega p. Can you see the trend here? Lithium and sodium, these are monovalent, right? They both, N is the same, but if you look at the expression omega p squared given by, so N E squared over M. So when N decreases, in first case N is the same, lithium and sodium have the same N, but this one has higher M, right? M is in the denominator. That means your frequency should decrease. But when you come to, potassium also, potassium has slightly less, I don't know, yeah. Anyway, important thing is, when you come to magnesium, what happens? It's increase. That's because the mass is larger, but N is now much higher, right? Because magnesium, aluminum, they give much more electrons rather than one. So that's why it's all coming from this equation, right? It depends on N or M. If you keep same N, mass determines the energy. If it is otherwise, mass tells you, if you go to magnesium to aluminum, what is the difference? These are N1, I mean for one atom you have N equals 1. Here N equals 2 for this is a divalent, right? Aluminum is trivalent. That means N becomes higher when you go this order. So that's why this is increasing the mass depending on the ratio, right? N over M ratio. If N increases, omega p increases, M increases, omega p decreases, right? So that's, you can see the trend. Okay, so that is basically the plasmons. Okay, so now, so far we were talking about different properties of free electron gas. Now let's look at heat capacity coming from free electron gases. So we talk about heat capacity coming from phonons, right? So that's basically, remember, T cube for low T and 3R for high T. So if you take an insulator, right, diamond, so entire heat capacity comes from what? Phonons, because diamond is an insulator. There are no free electrons. But if you take a metal, so you have enough electrons, right? That means if you have, suppose you have the material here, if I heat this N, high T, this heat has to propagate to the other end, right? So if you don't have free electrons, only way electron can be transported is through these phonons, right? Because they can make the atoms vibrate, that means you have phonon coming here. But if you have electrons, this heat can be transported by electrons, get the energy, then they get higher kinetic energy, they can move from one end to other end. That means heat can be transported by both phonons and electrons. But if you have insulator, it can be only by phonons. So if you use a very simple argument like we did before, if I take a three-dimensional, like one atom, so we have how many degrees of freedom? 3, right? So in the 3 directions. So then we can calculate the total energy. Equipartition theorem says it has 3 over 2 kT, right? Because 1 degree of freedom has half. Then if you get 3 degree of freedom, you have 3 kT. So now if you calculate total energy, N is the total number of electrons, that's the total energy, right? So then if you per mole, if you do this one, K becomes R. So this 3 over 2 RT, that's the total energy. Then what is the heat capacity? Take the temperature derivative, then you get 3 over 2 R. That's the classical way to look at that one, right? Because in this case, you don't have to consider the vibrations, right? Because these are electrons only getting the kinetic energy, only V squared. When we had the phonon, remember we got 6 here. Because why? You have 3 potential energies also, right? 3 terms from the kinetic energies, 3 terms from the potential. Because that's a harmonic oscillator, right? But in this case, electron is only not vibrating, they are moving. That's why we had. What is the value we got for the oscillators? 3R, right? Because you have to consider the potential energy also. Now that is the classical value for the heat capacity from electrons, not from phonons. So, but when people measured the heat capacity for metal, what they found was only it is very little bit more than 3R. 3R plus smaller number. If this is true, it should be 4.5R, right? 3R plus, you have 1.5R R value. That means you should have 4.5R. But people found that value is only little more than insulator value. Insulator value means 3R, right? So that means this is not really accurate. So then why do you think that is not true? Because basically we have to consider the quantum mechanical concepts, right? So if you want to get this, that's why we have to consider this free electron gas. But to consider, because if you are looking at the heat transport, means you are not looking at 0 Kelvin approach, right? So if you look at 0 Kelvin, that means low temperature. If you look at your probability of filling any state, suppose this is what in the free electron gas up to EF it is filled, right? That means what is the probability until you get to EF? What's the probability of filling any of this state? 1. Because any state here is filled. So this is the probability of filling any given state at this energy. This energy is below EF, right? So this state is always filled. What is the probability of filling any of these states? 1 up until you reach EF. This is 1. This is 0. At EF also you have probability 1. What is the probability of filling this one? 0. That means your probability function is simply this one. Right? All the states here is empty, all the states here is filled. But this is only true for low temperatures. If we have a finite temperature, the probability of filling any of these state is given by this special function. This is the most important thing for finite temperature. That is called the Fermi-Dirac distribution. The filling of states is actually, if you go very low energies, they are still filled, right? But something closer to this EF, they are not really. These states can be, some of this electron can be excited to higher state. That means this is not completely filled or this is not completely empty. So that is the probability of filling any state closer to this EF is given by this expression. This is called the Fermi-Dirac distribution. Fermi-Dirac distribution is given by 1 divided by this E, this X energy, that's the energy of this given one, minus EF times, we are called beta. Beta means 1 over kBT. That's the plus 1. That is the Fermi-Dirac distribution. So you can see, if you don't have one, what happens? This is more like Maxwell's-Boltzmann, right? Remember, Maxwell's-Boltzmann distribution function was E minus E over beta times E, right? So here, if this is minus 1, we'll talk about later, that is Gauss-Einstein distribution. These three are the three different things. One is for Fermi-Dirac distribution, then you have minus 1 Maxwell-Boltzmann. That's it basically, if we have, because electrons are all fermions, right? That's why they follow this Fermi-Dirac distribution. So later we will find if they are bosons, they follow different distribution. This is the important thing to remember. Please look at this one. 1 plus E minus E minus EF divided by KBT. Beta means KBT. It's easy to write this way, right? Yeah. Okay, so this is a very important function. Actually, if you draw this function, you can see this F Fermi-Dirac versus E. Suppose if you are, suppose that this is my EF. Suppose if EF, your E is greater than EF, that means much greater than EF, then what happens? If E is greater than EF, that means this is positive, right? So that means 1 plus very large number. 1 over very large number means it becomes 0. Suppose E is less than EF. That means what is this function? This becomes negative number, right? That means you have E negative large number. That means 1 over large number means infinity. So sorry, 0. That means it becomes 1 over 1. That means that becomes 1 here. But anything very large here, it becomes 0. Anything much away from EF, that becomes still 1. But when you come closer to this one, that's where things starting to change. You will find this one is going like this. This is the shape of the Fermi-Dirac function. So how was it for 0 Kelvin? It was simply this one. This was the 0 Kelvin. But for finite temperature, it is like this. What is this value? E equals EF means this becomes e to the power 0 means 1. 1 plus 1 is 2. That means half. This is exactly half. This is 0. This is 1. This is half. So now if you do for different, so this has beta, right? Beta has 1 over this KBT value. But remember this KB is called the Boltzmann constant, right? So T is here. So if you do for higher temperatures, still doesn't matter what the temperature, it should always go through this half. It doesn't matter, right? Only difference is if you go to higher temperature, it happens like this. If you go to even higher, like this. But always it should go through this one. So what does this mean? If it is low temperature, it can be like this. Goes like very little, but still has to go through like this. What is this really telling you? This is EF, right? That means the states closer to the EF. So it doesn't matter if it is too low or if it is too high. That means too high means it's 0. Too low means it's close to 1. But closer to this EF, some electrons can move from here to here. That's what happens, right? In this temperature, these electrons, this part will come to this part. If it's a higher temperature, this much can come to this one. You can see how it is moving from 1 to 1. So this is the important thing. So density of state is what? Density of state means how much states are available for you, right? So, but not all the available states are going to be filled. The Fermi-Dirac distribution says what are the states going to be filled. So density of state will tell you all the how much states, how many states are there for you to have your electrons. So density of state means number of states available, right? This basically dNO dE for a given. But not all the states are going to be filled. But if you multiply by the Fermi-Dirac distribution, that will tell you exactly how many electrons are there. If it's 0 degree, all the states are filled right up to EF. But finite temperature, Fermi-Dirac distribution will tell you out of those available states, how many states are going to be filled. That's the difference. You can follow through here. Everything I talked about here. Yeah. So this, please read this one carefully. Fe specified under equilibrium conditions, the probability that an available state at an energy E will be occupied by an electron. That's the probability distribution, right? So you density of state will tell you, for example, typically your N we wrote as dE, right? Is this true for finite temperature? This is only true for 0 temperature. If you want a finite temperature, you have to multiply this by Fe. Then you get the total number of electrons, right? Because in the 0 temperature, Fe is 1. Right? But finite temperature is not 1. So you have to multiply by. Please remember, if you want to calculate N, dE is not the total number of electrons. So you have to multiply by Fe. That tells you how many of those states are going to. This is basically Fe times dE. Because dN is typically dE times dE, right? This will tell you the available states, but the total number of electrons will be whether they are occupied or not. You have to multiply by Fe. That's the difference. Yeah. So everything I said you can follow here. Here is the for 6 Kelvin. So this is the finite temperature. Yeah. This is clear for everybody, right? You can say we have to be careful when you do this one. If you are doing this way, it's a positive function, right? If you are doing at this side, this is a negative number. E is less than EF. That's why then one know. That's how you get. Is that clear for everybody? You can. Okay. So now, if you want to get the this is very important graph. So if you draw, actually I can show here. So this is the density of state, right? So let me draw this one. So this is my density of state as a function of E. This way, right? Square root of E. So how do I draw Fe? Fe as a function of E. That is basically, this is EF. So this will be like this, right? For this finite temperature, this is half value. Now, if you want the number of electrons in the system, you have to multiply these two, right? So N is density of state times the function, because this means states, but this will tell you whether those states are filled or not. So now if you calculate the N as a function of E, you have to multiply this by this one. When you multiply, what do you get? Here you multiply this one by 1, right? That means you get the same curve. Because this is 1. Any function, if you multiply by 1, you get the same value, right? That means up to here I get same curve, then here it's going to be different. So now this one is increasing, but this is going down. If you multiply, you will find this is actually coming down like this. So this will tell you, get the idea here. So it was going like this. Now just multiply two curves, you know how to do that, right? So actually then what is this means? This is the stage below your EF. So these electrons are now here, that's all. So previously, so you didn't have any electrons in this region, 0, okay. Now you have this many electrons actually populating states above this one. That's it. That means I can write N as E times this one. Should be clear, right? So this is set T equals 0 like this right here, because this one, but any higher temperature, it should do this one. Okay. So then also it's very important to know how this Fermi-Dirac function properties. Actually, this one I got here. N means actually Fe. Please remember, Nk means Fe. So that is same thing, right? E minus E. This means Ef. So if you look at this one, this is the curve, right? If you take the derivative of this one, what do you get? If you take the derivative, you can see what is the derivative of this one? 0. That means you have 0 here. But here, this negative derivatives, that for that reason I take negative of this one. That means you get positive value. Then you get here at this point you have maximum, then it is going to decrease, right? So then you can see like this negatively. So if you take the Fe, typically your Fe as a function of E is this one. If you take the dF over dE as a function of E, actually I take negative of that one. So this value is, here it is 0. At this point, this shows very sharp peak like this. Ideally it is like this, negative, right? This is really negative. So but I take the negative of that one to show. So you can see this width depends on your temperature. So that depends on your temperature. If you decrease your temperature, this becomes narrower. So I'll give a homework problem to find some properties of this Fermi-Dirac distribution. This width proportional to Fermi energy and also temperature. If the temperature is higher, this width becomes larger. This is very useful sometimes when you do some integrals using this Fermi-Dirac distribution. That's a complicated function to do an integral, right? So you have to do some kind of approximations. So sometimes it's easy to use this function to make, then it becomes real simple. Yeah, clear? Please remember this N means really this Fe, right? So this is function of E. So this mu means Ef. Okay, so this is what we were talking so far, right? Yeah. So, okay, now let's, if I want to calculate in now quantum mechanically, if you want to calculate the heat capacity, now how do we do that? So again, if you want to calculate the total energy, so you have to calculate the total energy is E times your dE times Fe times dE, right? That's the total energy. So this is the energy of a given state, but that has the density of state given by this one, but that state is filled by this probability. That's the total energy. So this E times Fe NE or DE. So sometimes I write DE for NE, doesn't matter, just instead of state. Now, if you do this one, what do you get? E, FE you can write as one, no, this one, NE, if I write like this, but we know that NE, right? That is actually that three-dimensional or two-dimensional, whatever the way. So now if you want to take the derivative of this one, you know how to do that one. This very difficult integral to do actually. so but in the next slide I will show that one. If you do this integral, so you can get this answer. This C electron is given by pi squared dou 3 kb squared density of 10 times T. Remember in metals, heat capacity changes as linearly as T. So phonons, it changes T cube and constant, right? But for electrons, your the heat capacity changes as T. That's very important. If you write the total C, I can write it as some constant times T plus another constant times T cube if it is low temperature, right? Like this. But this is the free electron gas contribution, this is the phonon contribution. If you go to low temperature, this part becomes small because phonons are going to be less, right? Low temperature means your phonons are less, then mostly governed by this linear dependence. But how do you do this integral? This is pretty complicated. There are a lot of tricks how people have done. I'll just show you how it was done. So this is what we had, right? So this is pretty neat trick actually. This is what you have to calculate total energy, right? E times D times Fe. If I plug in this one, so then you take the derivative with respect to this one. So this is the trick. Your integral limits are 0 to infinity. So here this E you replace with E minus EF. Reason is if you take EF times this integral, so this is basically dE, this one is dN over dt because n is given by this dE times Fe, right? So this function, since EF is a constant, dN over dt means what? If you have some total number of electrons, if you temperature, even if you change the temperature, number of electrons don't change, right? That means dN over dt is really 0. That means if I put additional EF, that means this total integral is like replacing with 0, right? So that's the whole idea. So if you do that one, now you can approximate to this dE as dE at the Fermi energy, then this becomes the EF. This is easy to do the integral. So we know how to take dF over dE because F, you know how to do that, right? F is 1 over E minus dF plus 1. You know how to get the dF over dE, right? Take this one time this one, then this divide by square of this one, right? If you do that one, you get this function, is basically. So then if you do few steps here, so then you make some substitution, then energy, this limits also changes. But we have to make one assumption for this EF for this K is larger than KBT, then you can replace this function by minus infinity. So because if it's a finite limit, if you have say EF something, so this is impossible to do. But if you can make this one minus infinity, this is a standard integral. So that's what you get, minus infinity to infinity, this function, this is a standard integral. If you do that one, you get that answer. Because I don't expect you to know, but it's good to know how this kind of integrals are done. So these are all standard steps, right? Only difference is you just make this integral limits to minus infinity in that limit, and this is the standard integral. So important thing is that the CV depends on directly linearly with T. But we can do very simple estimate here. So let's do that one. So by doing all these integrals, we got pi squared over 3 kb squared, this one, right? So let's make a very simple approximation. Suppose only the electrons from here to here are excited, right? So now you can calculate the total energy coming from that electrons. So typically this range is about kBt energy. kBt is energy, right? That means this whole range you can show. That's what I'm going to give it for homework problem. So to show this is 2 kBt times. So that means you want to only consider energy range in that 2 kBt. Others don't change. So that means your only energy you need to calculate is, this is the total number, the density of states times your energy is coming from only 2 kBt times the Fermi energy. That's the total number of electrons, right? So then if you, total number of electrons times the energy, that will give you the total energy. So now if you no, this is the total number, yes, yeah, total number of electrons, then you have to multiply by your classical value of each electron has 3 over 2 kBt. So if you do that one, you get, this is the value. So now that's the total energy. Don't worry about this E0. If you take the temperature derivative, you can see 2T, 2 cancel, you get 3K squared, this value. Look at these two, is pretty much, this is what we got doing that tedious integrals, right? So what is pi squared over 3? About 3, right? So that's what you are getting here. It's not a bad estimate, right? See how simple it is? Because we know only the electrons close to the Fermi energy are the ones contribute to the thermal conduction or even electrical conduction. So if you do that one, you get them. So then the total capacity is given by this one. So you can see people have measured this one. So since C is this one, you can plot C over T as alpha plus beta T squared, right? If you plot C over T versus T squared, you should see a straight line, right? So this is what you have here. So many materials, T squared, C over T, you can see how nicely they follow this one. Here are some of the experiments and the free electron, the heat capacity using that pi squared over 3, that whatever the value. If you calculate, you can see the theoretical value and the experimental value. They are not exactly correct, but they are close enough. It's like with experiment, metals. Yeah. So I will explain later. I think we have defined something called the effective mass. So, but overall, they are reasonable numbers, like this, maybe 0.6, 0.5. Yeah, not too bad, right? But this one follows the same way. Okay, so that we discuss about the thermal conduction of electrons. So last thing I want to talk is the electrical, the charge conduction or the electric current in free electron gas. That is probably leads to the semiconductors and all these things. If I apply some electric field, what happens to these electrons? So this is we call the derivation of Ohm's law and the Hall effect, quantum Hall effect, and all these things we can talk about. This one. Basically, I think we already discussed about this one. I have a few more minutes. Right? Yeah. So basically, if I have this free electron gas, if I apply some electric field, I explain to you what happens, right? So this electron is getting this force, then it starts to accelerate. Accelerate means its velocity should go increase infinitely, right? But it doesn't happen because once it is accelerating, it's going to collide with the ion. Then immediately that velocity goes to zero. We call that, anybody remember? That's called the relaxation. So this approach is called the relaxation time approximation. So we have electron, when I apply electric field, that means applying some voltage source, right? You have, then these electrons are going to accelerate, it collides and goes to zero, then again going to accelerate, goes to zero. That's the approach we are doing. So that means you can write your, for a given electron, that is the second law, equals electron time force, then we call that force due to that collision is called the collision time. This is the most important thing, that collision time, that force is given by this relaxation time approximation, your change of your momentum divided by the relaxation time. So that's the difference. But what is delta P? Delta P is actually mv minus 0, because it goes to 0 immediately, divided by tau. That's the key thing here. You can see here, this, that is the total force, but this is the force due to the collision. This is called the relaxation time approximation. We'll start from there in next class. Okay. So I'll see you Thursday. Okay. So now we finished talking about heat conduction. Now we are going to talk about electrical conduction. This is interesting. We talk about the Hall effect, quantum Hall effect, and all interesting stuff.